Hello, this is a rehearsal of my qualifying exam. My title is The Coexistent State of Superconductivity and Spin Density Waves in Cuprates and Pnictides. This is the outline of my presentation. I'll give a short introduction to the high Tc superconductors, and this includes the cuprates and ion-based pnictides. I will give an introduction to the coexistent state of superconductivity and spin density waves. And I will show you the model that I used, the results from the model, and the prospective future work. There are two criteria for superconductor to exist. It must have zero resistivity, and it must exhibit the Meissner effect. A material that has zero resistance but no Meissner effect is the perfect model. We will not call it a superconductor. People divide superconductors into two subgroups, conventional and unconventional, according to the superconducting pairing mechanics. The conventional superconductors have S-wave symmetry, and the examples, which means the gap symmetry is a constant. The examples are the simple metal like mercury, aluminum, and lead. Also, Nb2 is also considered a conventional superconductor, and the mechanism of superconductivity in these materials can be explained by BCS theory. It's mediated by electron and phonon interaction. The superconducting gap function is a constant in these materials. Unconventional superconductors contain heavy fermions, organic superconductors, and high Tc superconductors. The mechanics of superconductivity cannot be explained by BCS theory. And the two high Tc superconductors, cuprates and pnictides, are the focus of my research. So let's take a look at the cuprates. The parent compound of a cuprate is an insulator, and they will change properties upon doping or under pressure. The supercurrents will only flow on the copper dioxide plane. From the fast diagram, when we apply doping, the anti-magnetism will disappear, and on the whole dope side, the anti-magnetism disappears quite abruptly. However, on the electron dope side, the anti-magnetism disappears rather slowly. The dashed green line indicates the pseudo-gap phase transition. The origin of the supergap is still not clear. There is a spin glass on the whole dope side, which is not shown in this phase diagram. But it's not the spin density wave has never been detected on the electron dope side. But for the coexistent state, it only happens in the electron dope side. It's never been detected in a whole dope side. The light green region is the possible area for nail temperature. People still don't know what exactly causes the asymmetry in the phase diagram. It's a very intriguing question. The crystal structure shows that for the electron-doped materials, there is no apical oxygen. If we know the cause of the asymmetry, maybe we will know what the mechanics of the unconventional superconductors is. Another difference is the coexistence of the superconductivity and spin density waves. If we understand what's happening in this phase, we may know why the phase diagram is different on each side of doping. This is the case in the cuprate materials. Now let's look at the situation in the iron-based superconductors. So the superconductors in neckties have a lot in common with the cuprates. They all have two-dimensional structure, and like the cuprate, the superconducting current is only flow on the iron arsenic layers. Like the cuprates, there are different crystal structures for the iron-based necktie. Iron-based materials, we can divide. They have different structures, and we can divide them into 5 different subgroups by their chemical structures. Different structures have different properties. The 122 family is the easiest to synthesize, and it's the most studied material. It's the most studied iron-based material, superconductors. And there is evidence of spin density wave and superconducting coexistence state, which have been detected in this 122 material. We will use the 122 material as our focus. The temperature doping phase diagram of 122 has been well studied. Again, like the cuprates, it changes its property with doping. The parent compound is a metal with antiferromagnetic spin density waves. When the doping increases, the antiferromagnetism decreases. At some specific value of doping, the superconducting state starts to show up, and the Tc of superconductivity starts to continue to go up until it reaches an optimal doping value. Then it starts to decrease with doping. The phase diagram shows a clear crossing over of spin density wave and superconducting state. This narrow region is where I will invest my precious time. Next, let's take a close look at this small region. First, let's see what is the spin density waves. If the Fermi surface nested with other part of the Fermi surface, there will be instability. The name of spin density waves is quite descriptive. It's a periodic modulation in density of the electronic spins. The period of this wave is described by a wave vector q. If the wavelength is a fraction or multiple of the lattice constant, then we say the density wave is commensurate. Otherwise, it's incommensurate. The spin density wave is first observed in chromium, and it has been found in quasi-1D organic conductors or some low-dimension materials. It can be observed by neutron scattering or susceptibility measurements. The spin density waves have been discovered in different superconductors, such as heavy fermion superconductors, organic superconductors, and electron-doped cuprates and iron nuclides. The spin density waves have been discovered in different superconductors. This paper by Pratt shows the evidence of the coexistent state of spin density, antiferromagnetism, and superconductivity. These three panels show the magnetization, resistivity, and integrated intensity of nuclear reflection. The resistivity tells us the TC transition. The nuclear reflection signal half-half 1 is the same for the parent compound, which is considered to be the antiferromagnetism stripe structure in all iron arsenic materials. Therefore, the signal can tell us the evolution of the antiferromagnetism order. We can see that when T is lower than when temperature is lower than Néel's temperature, the signal starts to grow. When it's even lower than the superconducting temperature, the signal is reduced, which reveals the competing nature of antiferromagnetism and superconductivity. In this paper, it also argued that the existent state is quite homogeneous. Next, I'll